e to the x and the natural log of x. We begin with a definition of the number e. We define e to be the limit as p goes to infinity of 1 plus 1 over p to the pth power. A typical proof of the existence of this limit amounts to showing that the quantity 1 plus 1 over p to the pth power is increasing for all positive p, and that the quantity never exceeds 4. It turns out that this limit is an irrational number that's approximately equal to 2.71828. Now, a good way to think of this is to think of the graph of y equals 1 plus 1 over p to the pth power versus p. It's the graph of an increasing function with a horizontal asymptote at the number e. Now, given this number e, we can talk about the exponential function with base e. This is just an ordinary exponential function, much like 2 to the x or 3 to the x. In fact, the graph of e to the x lies between the graphs of 2 to the x and 3 to the x. It's an increasing function for all x. Its values are between 0 and 1 for negative x. Its values are greater than 1 for positive x. And notice that we have the points 1, e on the graph, as well as the point 2, e squared, and so on. Now we're going to state here as a theorem 3 important facts about the exponential function e to the x. First, for any number x, e to the x is equal to the limit as p goes to infinity of 1 plus x divided by p to the pth power. Second, an important limit. The limit as h goes to 0 of e to the h minus 1 divided by h is equal to 1. And third, the derivative of e to the x with respect to x is equal to e to the x. Now let's look at a proof of the first part of our theorem. That is, e to the x is equal to the limit as p goes to infinity of 1 plus x divided by p to the pth power for all x. Now remember that this is true when x is 1 by definition. Now we'll first show that it's true when x is equal to minus 1. Observe that 1 plus 1 over p can be rewritten as p plus 1 divided by p, and e to the minus 1 is the reciprocal of that quantity, and the reciprocal of that limit is equal to the limit of the reciprocal, p divided by p plus 1 to the pth power. Now let's make a simple change of variables here. Let's let q equal p plus 1. Then p is equal to q minus 1, and so this is the limit as q goes to infinity of q minus 1 divided by q to the q minus 1 power. Now q minus 1 over q is equal to 1 minus 1 over q, and we can factor off 1 minus 1 over q to the minus 1 power. The limit of the second factor is clearly 1, since 1 over q approaches 0 as q goes to infinity, and so this is the limit as q goes to infinity of 1 minus 1 over q to the qth power, and we may as well go back to the letter p instead of q here. So this says that e to the minus 1 power is equal to the limit as p goes to infinity of 1 plus negative 1 over p to the pth power. So the statement is true when x is equal to minus 1. Now let's consider an arbitrary positive x, and let's consider e to the plus and minus x at the same time. E to the plus or minus x will be either e or e to the minus 1 raised to the x power. And we know that e or e to the minus 1 is equal to the limit as p goes to infinity of 1 plus or minus 1 over p to the pth power, all to the x power. Now we can bring the x power inside of the limit and rewrite this as the limit as p goes to infinity of 1 plus or minus 1 over p to the p times x power. Now we're going to replace p times x with q. That means that p is equal to q divided by x, and so 1 over p is x divided by q, and this becomes the limit as q goes to infinity of 1 plus or minus x divided by q to the qth power. Now we're essentially done. We can replace the letter q with p again, and we now know that e to the x is equal to the limit as p goes to infinity of 1 plus x divided by p to the pth power for all x, positive or negative. And of course this is obviously true when x is equal to 0, since it says 1 equals the limit as p goes to infinity of 1 to the pth power. Now we're going to give an outline of a proof of part 2 of our theorem that the limit as h goes to 0 of e to the h minus 1 divided by h is equal to 1. We begin by looking at the quantity 1 plus h over n all to the nth power minus 1 divided by h, where n is any positive integer. Notice that as n goes to infinity, the first term in the numerator, 1 plus h over n to the nth power, will approach e to the h by part 1 of our theorem. If we expand that first term in the numerator using the binomial theorem, the first two terms will be 1 plus n times h over n, or 1 plus h. And so when we subtract 1 and divide by h, our first term ends up being 1, and it turns out the second term is n minus 1 over 2n times h, and we have higher order h terms up until 1 over n to the n times h to the n minus 1. Now don't worry if it's not completely obvious why those coefficients are the way they are. Just notice that the coefficient of h there is less than or equal to 1/2 for all n. It turns out that if h is between 0 and 1, all of the h terms here combined are less than or equal to 1 times h for all n. Also, it's clear that for positive h, the entire quantity is greater than 1, and so we have that 1 plus h over n to the nth power minus 1 divided by h is between 1 and 1 plus h for all n greater than or equal to 2 and all h between 0 and 1. Now, since that inequality is true for all n greater than or equal to 2, when we take the limit as n goes to infinity, we find out that e to the h minus 1 divided by h is greater than or equal to 1 and less than or equal to 1 plus h if h is between 0 and 1. And so now it follows very easily that the limit as h goes to 0 from above of e to the h minus 1 divided by h is equal to 1. Now what about the limit as h goes to 0 from the left? That's equal to the limit as h goes to 0 from the right of e to the minus h minus 1 divided by minus h. Now let's multiply the numerator and denominator there by minus e to the h. Minus e to the h times minus 1 gives us an e to the h, and minus e to the h times e to the minus h equals minus 1, and the denominator is h times e to the h. Now the e to the h factor in the denominator clearly approaches 1 as h goes to 0 from the right, and so this limit is the same as that of e to the h minus 1 divided by h, which we've seen is equal to 1. And so we're done. We've glossed over a few details, but this is the idea of the proof. Now all the hard work has been done. We're ready to prove now that the derivative with respect to x of e to the x is equal to e to the x. The definition of the derivative says this is going to be the limit as h goes to 0 of e to the x plus h minus e to the x divided by h. We can factor e to the x from the numerator, and we can also bring the e to the x outside the limit since it doesn't depend on h. So now we have e to the x times the limit that we just proved is equal to 1. So the derivative of e to the x with respect to x is e to the x. So we now know that the derivative of e to the x with respect to x is equal to e to the x. When we combine that fact with the chain rule, we have that the derivative with respect to x of the e to the u equals e to the u times du dx. The key thing to understand here is that e to the u is a composition with u playing the role of the inside function. So to differentiate a function of this sort, e to a power, you simply multiply the function by the derivative of the exponent. Let's look at a few examples. Let's take the derivative with respect to x of e to the minus x squared. Here the outside function is e to the u, and the inside function u is minus x squared. So we have e to the u, or e to the minus x squared, times the derivative of minus x squared, which is minus 2x, and so we have minus 2x times e to the minus x squared. Let's take the derivative with respect to x of x times e to the minus 2x. Here we need to use the product rule. We have 1 times e to the minus 2x plus x times the derivative of e to the minus 2x, which is e to the minus 2x, times the derivative of minus 2x, which is minus 2. Now we can factor e to the minus 2x here, and the other factor is 1 minus 2x. Let's take the derivative with respect to x of 1 over 3 minus 2 e to the minus x over 2. Now let's think of our function as 3 minus 2 e to the minus x over 2 raised to the minus 1 power. Differentiating the outside function here gives us minus 3 minus 2 e to the minus x over 2 all to the minus 2 power. Now we multiply by the derivative of the inside, which is going to be minus 2 times e to the minus x over 2 times the derivative of minus x over 2, which is minus 1/2. So we have minus a quotient with 3 minus 2 e to the minus x over 2 quantity squared in the denominator, and the numerator is simply e to the minus x over 2. The natural logarithm. The natural log function, abbreviated by the letters Ln, is defined to be the base e logarithm. The natural log of x equals log base e of x. In other words, the natural log function is the inverse of the exponential function e to the x. The natural log of e to the x equals x for all x, and e to the natural log of x is equal to x for all x greater than 0. Both of these statements essentially say that the natural log of a number is the power that e is raised to equal that number. Since e to the x and natural log of x are inverses of each other, their graphs have the same relationship to each other that any pair of inverse functions have, and that is that each is a reflection of the other about the line y equals x. Since natural log is the base e logarithm, the natural log of e is equal to 1, or in other words, the natural log of e equals 1 because e to the first power equals e. Also notice that the natural log of 1 is equal to 0 because e to the 0 equals 1. Now let's find the derivative of the natural log function. Let's first write the equation y equals natural log of x, and then raise e to each of those powers. E to the y equals e to the natural log of x, which is x. Now let's take the derivative of both sides with respect to x. Using the chain rule, on the left side we have e to the y times dy dx, or y prime, and on the right side we just have 1. This says that y prime equals 1 over e to the y, but e to the y equals x, and so this equals 1 over x. Therefore, the derivative with respect to x of the natural log of x equals 1 over x. Combined with the chain rule, we have that the derivative with respect to x of the natural log of u equals 1 over u times the derivative of u with respect to x, which we can also write as u prime divided by u. So notice that when taking the derivative with respect to x of a function of the form natural log of u, we get a very special type of quotient, one in which the numerator is the derivative of the denominator. Now let's look at a few examples. Let's take the derivative with respect to x of x times the natural log of x. We'll use the product rule. We have 1 times the natural log of x plus x times the derivative of the natural log of x, which is 1 over x. And so we end up with natural log of x plus 1. Let's take the derivative with respect to x of the natural log of cosine x. Here we use the chain rule. Since the derivative of the natural log of x is 1 over x, the derivative of the outside function takes the form of 1 over cosine x, and then we multiply by the derivative of the inside function, cosine x. So we have 1 over cosine x times minus sine x. Now notice that this is equal to minus tangent x. Now let's take the derivative with respect to x of the natural log of the absolute value of x. We need to consider separately positive and negative x. If x is greater than 0, we just want the derivative with respect to x of natural log of x, and if x is less than 0, we want the derivative of the natural log of minus x. So for positive x, we now have the derivative 1 over x, and for negative x, we use the chain rule and write 1 over minus x times the derivative of minus x, which is minus 1. So notice that the derivative turns out to be the same in both cases. In fact, the derivative here is 1 over x for all x not equal to 0. Notice that by composing the natural log with the absolute value function, we extend the domain of the natural log, which is just positive x's, to all x not equal to 0. And the derivative of this function, which is defined for all x other than 0, is 1 over x. Now let's take the derivative of the natural log of the absolute value of x minus 1 divided by x plus 1. Now we've just learned that the derivative with respect to x of the natural log of absolute value of x is just 1 over x. So the first thing we need to do here is to simply write 1 over the quantity inside the absolute value. That's just the reciprocal x plus 1 divided by x minus 1. And then we multiply by the derivative of the inside function, x minus 1 over x plus 1. For that, we'll use the quotient rule. The denominator will be x plus 1 squared. The numerator will be 1 times x plus 1 minus 1 times x minus 1. Notice that numerator is x minus x plus 1, which equals 2. Also notice that we can cancel an x plus 1 factor, and we end up with 2 divided by x minus 1 times x plus 1, or 2 divided by x squared minus 1. Now let's look at a quick review of the algebraic properties of exponential functions and logarithms in the context of e to the x and the natural log of x. The following are really just simple properties of exponents. E to the x plus y is equal to e to the x times e to the y. E to the minus x is equal to 1 over e to the x. E to the x minus y equals e to the x divided by e to the y. And the pth power of e to the x is e to the x times p. Four analogous properties of the natural logarithm follow from these. The natural log of x times y we can rewrite as the natural log of e to the natural log of x times e to the natural log of y. And now that product of powers of e can be rewritten as e to the natural log of x plus natural log of y. And now the natural log of e to that power equals the power, and so we have the natural log of x plus the natural log of y. So the natural log of a product equals the sum of the natural logs of factors. In the natural log of x divided by y, let's again replace x with e to the natural log of x and y with e to the natural log of y. And now by a property of exponents, this is the natural log of e to the natural log of x minus natural log of y. And since this is the natural log of e to a power, it's equal to the power, which is natural log of x minus natural log of y. So the natural log of a quotient is equal to the natural log of the numerator minus the natural log of the denominator. Let's also notice that there's a very important special case of this when x equals 1. It says that the natural log of 1 over y is equal to the natural log of 1 minus the natural log of y, but the natural log of 1 is 0, and so that's just minus the natural log of y. So the natural log of 1 over y equals minus the natural log of y. The natural log of x to a power p is equal to the natural log of the pth power of e to the natural log of x. E to the natural log of x to the pth power is equal to e to the p times the natural log of x power. And again, we have the natural log of e to a power, so we get the power, which is p times the natural log of x. So the natural log of x to the p equals p times the natural log of x. Now let's talk a little bit about base conversion. Turns out that an exponential function with any positive base can be rewritten as an exponential function with base e as follows. B to the x is equal to e to the natural log of b to the x, and by the third property of the natural logarithm, that's equal to e to the x times the natural log of b. So we simply convert the base from b to e by multiplying the exponent by the natural log of b. Also, you're probably already familiar with the conversion formula for logarithms. For conversion from log base b to the natural log of x, we have log base b of x equal to the natural log of x divided by the natural log of b. Now to see why this conversion formula is true, first notice that it's equivalent to natural log of b times log base b of x equals natural log of x. By the third property of the natural log function, we can move the log base b of x factor inside as an exponent, but b to the log base b of x is just x, and so this is the natural log of x. Other bases. Let b be greater than 0. Then b to the x equals e to the natural log of b to the x, which equals e to the x times the natural log of b. Therefore, the derivative with respect to x of b to the x is equal to e to the x times log b times the derivative of x times log b, which is log b. Now let's rewrite e to the x times log b as b to the x, and we have the formula b to the x times the natural log of b. So this says that we take the derivative of any base exponential function in much the same way that we take the derivative of e to the x, in that it's the function itself times the natural log of the base, and in the case where the base is e, the factor log b is equal to 1. Also, since log base b of x equals the natural log of x divided by the natural log of b, we know that the derivative with respect to x of log base b of x is going to be equal to 1 over the natural log of b times the derivative of the natural log of x, which is 1 over x. So we have 1 over x times the natural log of b. So this is very much like the formula for the natural logarithm, only it's divided by the natural log of b. Examples. The derivative with respect to x of 10 to the x power is equal to 10 to the x times the natural log of 10. The derivative with respect to x of 2 to the minus x is equal to 2 to the minus x times the natural log of 2 times the derivative of the inside function minus x, which is minus 1. So we have minus 2 to the minus x times the natural log of 2. The derivative with respect to x of 1 over 1 plus 2x is the derivative of 1 plus 2 to the x to the minus 1 power, so we have minus 1 times 1 plus 2 to the x to the minus 2 power times the derivative of 1 plus 2 to the x, which is 0 plus 2 to the x times the natural log of 2. The derivative with respect to x of x times the common log of x, that is, log base 10 of x, is 1 times common log of x plus x times the derivative of common log of x, which is 1 over x times the natural log of the base, which is 10. So we have common log of x plus 1 over the natural log of 10. The derivative with respect to x of the common log of x, using the chain rule, is 1 over common log of x times the natural log of 10 times the derivative of the inside function common log of x, which is 1 over x times the natural log of 10. So we have 1 over x common log of x times the square of the natural log of 10. Logarithmic differentiation. With the help of the natural logarithm, we can differentiate functions that have the form of an x-dependent base raised to an x-dependent power. For example, let's find the derivative of f of x equal to x to the minus x power, where the domain of this function is understood to be all positive x. Here's the graph of that function. To compute f prime, we'll first write y equals f of x, or y equals x to the minus x, and take the natural log of both sides. Then by a property of the natural logarithm, we have natural log of y equals minus x times the natural log of x. Now we differentiate each side of this equation with respect to x. The left side gives us 1 over y times dy dx by the chain rule, and using the product rule on the right side, we get minus the quantity 1 times natural log of x plus x times the derivative of natural log of x, which is 1 over x. So this is minus natural log of x plus 1. Now we simply multiply by y, and we have dy dx equals minus natural log of x plus 1 times y, but y is x to the minus x, so we have minus natural log of x plus 1 times the original function x to the minus x. So notice there are 4 steps here. First write y equals f of x, take the natural logarithm of both sides, then differentiate both sides with respect to x, And finally, multiply through by y and replace y with f of x. Now that we have this derivative, we can learn something important about the graph of that function. Notice that the graph has a horizontal tangent line and a local maximum value at some number between 0 and 1. The derivative is 0 at that number, and our formula for the derivative tells us that at that number, the natural log of x equals minus 1. Now the natural log of x equals minus 1 if x is equal to e to the minus 1 power. So the derivative is 0 when x is equal to 1 over e. And so 1 over e is the critical number there, and the maximum value of the function is f of 1 over e, which is 1 over e raised to the minus 1 over e power, which ends up being e to the 1 over e power.